Hello there, my calculus people. Today we're going to talk about how we do an integration, so take an antiderivative using something called U-substitution. And it could have been any letter, literally. It could have been J substitution or any letter you want. Okay, but they decided to use U, who's they? I don't even know, way back in the hundreds of thousands of years ago, when they were when people were deciding what to do, right, to kind of make these things concise across all nations and whatever else. A bunch of guys got together and decided this is what they would call it. So here we go, U-substitution. So we know we're going to use U-substitution when we see a multiplication underneath your integral. Okay, so I have this part, which is your something to a power times 2x. So whenever we see multiplication, that's when we're going to try and use U-substitution. So what we do is we say, all right, I'm going to let U, this regular single variable U, be equal to, in this case, x squared plus 1. Okay, usually it's some type of an equation, right? So what's going on here is we have an equation raised to the 5th power and then times by what we could consider the derivative of the answer, right? So this is kind of undoing the chain rule. So if we think about chain rule, first we would take the derivative of the power, right? Subtract 1 from the power and then multiply it by the derivative of the inside. Well, 2x is the derivative of x squared plus 1, right? So it makes sense to link our more complicated algebra here, x squared plus 1, our U value. So then what we do is we take the derivative with respect to x. Okay, du dx is the derivative of x squared is 2x, and then derivative of 1 is 0. Okay, and what we do now, because we want to use substitution, notice there's a dx here in our integral. We want to solve this equation for dx. Okay, and when we do that, we get dx equals du divided by 2x. Right? Essence, and basically those guys switch. There, you multiply by dx and we divide by 2x. Okay, so now we have to do our substitution. We're going to actually replace. We're going to replace x squared plus 1 with u, right? X squared plus 1 is equal to u. So let's do this here. Equals the integral of u, right? No longer is it x squared plus 1. We are now calling that whole entire thing u. So u to the 5th times 2x. And now I'm going to replace dx with du divided by 2x. Okay, remember this is multiplication. So now I'm going to simplify. I know that 2x divided by 2x is 1. So I can, in essence, eliminate those two pieces from my integral. So I'm looking at the integral of u to the 5th du. So notice there's no more x in our integral at all. It's only the variable u, which is exactly what we want, right? This is super, quote unquote, super simple to do. It's going to use our one rule of integrals, which is add 1 to the power. So when we integrate, find the antiderivative of u to the 5th, that's u to the 6th power times 1/6 du. Okay, and then plus our constant of integration. We always have this plus c whenever we take the integral of an indefinite integral. Okay, so now that we've done that, we're going to go back in and replace u with what we started with. So u was x squared plus 1. Okay, so I'm going to raise that to the 6th power and put the multiply by 1/6 in the front because that's traditionally where it goes. So this is the antiderivative or the integral of what we started with over here. Okay, so what we want to do is let this random letter u be the complicated equation so that I get something that's really simple to take the antiderivative of. Okay, right? It's pretty complicated. It looks complicated, But this one over here, u to the 5th du, looks much simpler. Okay, so that's the gist of what we're doing here with u substitution. Okay, so looking at this next problem, notice that it has a multiplication, right? It's x squared times 2x cubed plus 5 raised to the 4th power. So let's let u, sorry I did this in blue, u is going to be 2x cubed plus 5. Okay, that's going to be our u that we're going to replace. Okay, so now we'll take the derivative with respect to u. Let's just do this. This is what teachers do. Okay, the derivative of 2x cubed is 6x squared, and the derivative of 5 is 0, so du equals 6x squared dx. Okay, this also makes our solving for dx pretty easy, because that's du divided by 6x squared. Okay, so if we put the dx over here after the x derivative, right, it just makes our anti-deriving life a little simpler. Okay, so let's go back and see. Okay, so we have the integral of x squared times, in this case, u to the 4th power. And instead of dx right here, I'm going to put du over 6x squared. So I've done my u substitution. I have substituted my equation with the letter u, and now let's see what I can divide out. How can we simplify? X squared simplifies with x squared. Okay, so then this 6 becomes a 1/6 product. So let's go back and let me rewrite this now. We have the integral of u to the 4th du all divided by 6. Right, because it's multiplication. So we multiply the du on top, we divide everything by 6. So what we're going to do to make this simpler is this is a constant of divided by 6 is a constant. So we're going to pull that divided by 6 out to the front by multiplying the integral by 1/6. So we're going to have 1/6 of the integral of u to the 4th du. Okay, so once again, hopefully you understand that this is much simpler, right? U to the 4th du is a lot more simple than x squared times 2x cubed plus 5 to the 4th, right? Much, much simpler. So let's go ahead and take the antiderivative of u to the 4th. So we have 1/6 still times the antiderivative of u to the 4th is u to the 5th times 1/5. Right, we have the power, we add 1 to the power, so 4 plus 1 is 5, and then you multiply by the reciprocal of your new power. And of course we have our plus c plus your constant of integration. So 1/6 times 1/5 is 1/30. We're going to replace our u. Once again, u was 2x cubed plus 5, so that goes back in here. 2x cubed plus 5. And that's being raised to the 5th power, and we have our plus constant of integration. Okay, so the point is that when I take this derivative, right, I bring the 5 out front and I multiply it, and then I raise it to the 4th power, and then I multiply by the derivative of the inside, and I reduce that. When I take the derivative of this function, I should be getting the beginning of my integral over here. Right, that's the whole point, is that if I were to take the derivative of this blue thing here, right, if I derived this, take the derivative of that, the answer should be this. Okay, that's what we're trying to do. Okay, what else do we have here? So once again, we have multiplication. So don't forget, we're going to make this a little bit easier. I don't know, easier, different. The square root is also known as raising something to the 1/2 power. Okay, remember we don't have an antiderivative for square root, but I do for a power rule. So make everything that we can into a power so that we can take the antiderivative. Okay, so I have x times this thing right here. So let's let u be x squared plus 3. Okay, so then du is 2x dx, and dx is du divided by 2x. Okay, so now I can do my substitution and replace these two parts of my integral. So that's the integral of, let's see, x times u to the 1/2 times du over 2x. Okay, there we go. Now we have to do our canceling, right? We have our x here, and we have divided by x. X divided by x is 1. And now I'm going to bring my denominator of 2 to the outside as a 1/2. So 1/2 the integral of u to the 1/2 du. Much simpler way to take an antiderivative. So 1/2, the antiderivative of u squared, we're going to add 1 to our power. 1/2 plus 1 is 3/2. And we're going to multiply by the reciprocal of our power. So the reciprocal of 3/2 is 2/3 plus c, plus that constant of integration. Now we multiply our fractions together. 1/2 times 2/3 is 1/3. It's 2/6, but 2/6 reduces to 1/3. Okay, we're going to replace our u. We're going to replace u with x squared plus 3. And a plus our constant of integration. So if we knew an initial condition, if we knew f of 1 equaled 3, right, we could plug a 3 into here. This was the f section, and we would replace x with 1. And you could solve for c to figure out what that exact constant is going to be. But that's not what we're asked to do. We don't know the initial condition, so we're not doing that just yet. Okay, one more time. Right, here we have a square root, and it's in a denominator, so even better. That means we're going to not have to the 1/2 power, we're going to have to the negative 1/2 power. Okay, so all of this, anytime we have this square root, that is being raised to the 1/2 power, but because it's in a denominator, it's being raised to the negative 1/2 power, because we want to have everything written as a power rather than any radicals. Okay, so we're letting u be 3x squared plus 4. Take the derivative, 6x dx, solve for dx. Okay, so now let's do our replacing. We're going to replace 3x squared plus 4 with u, and we're going to replace dx with du over 6x, because we still need to have this d something, the width of our little rectangles. So this is the integral of x times u to the negative 1/2 times du over 6x. We can divide x by x. We can bring the 1/6 to the outside of our integral. So we have a real simple thing to integrate. 1/6 of the integral of u to the negative 1/2 du. Okay, so we're still going to use our rule, and we're going to add 1 to our power. So if we add 1 to negative 1/2, that becomes a positive 1/2. And we multiply by the reciprocal and plus our constant of integration. So our fraction, 2 times 1/6 is 1/3. And let's replace u. What was our u? Our u was 3x squared plus 4. And that's being raised to the 1/2 power plus c. Okay, so if we want to, not that we have to, we can take our 1/2 power and rewrite it as a square root. So you might see it written like this on a multiple choice test or something, but this method with the 1/2 power is perfectly good. In fact, it's excellent. So you can leave it like that if you want to. So hopefully this helps with some U-substitution and how we take the integral when we have multiplication after your integral. All right, have a great day. See you next time.